In this problem, a veterinary clinic burns contaminated bedding and disposable supplies in its on-site incinerator. Stack tests of the incinerator gas show a measured CO concentration of 250 parts per million at 10% O2 on a dry basis, a measured CO2 concentration of 8,000 parts per million at 7% O2 on a dry basis. The EPA requires combustion efficiency reporting at concentrations of 7% O2 on a dry basis. The combustion efficiency is most nearly 94.5%, 96%, 97%, or 99.9%. So, the question is asking us for the combustion efficiency. If we search for this in the reference manual, it will take us to the following equation in Chapter 2 on air, where CE, combustion efficiency, is equal to CO2 over CO2 plus CO times 100%, where the volumes are in parts per million. So now, how do we get the values we need for both CO2 and CO? Well, we can see that CO2 is already given at 7% O2 in the problem statement. So we can use that term directly. So we're going to write here 8,000 parts per million over 8,000 parts per million plus CO. So, what about CO? There is another equation we can use from the reference manual as well. If we search for gas stream or 7% in the reference manual, this will bring us to the next equation just a little bit below the first equation. It's titled Correcting Particle Concentrations in Gas Streams for 12% CO2 and 7% O2. Knowing to look for this equation might not be obvious at first. You would have to recognize that 7% O2 or 12% CO2 are common reference conditions used in combustion and air emission problems, or that these are referred to as gas streams in regulatory language. If you didn't know that before studying, well, neither did I, and that's exactly why we study. So let's look at the equation as it's written here. It provides spaces for both CO2 and O2. Now, since our problem is only asking about O2, we can eliminate part of the equation related to CO2 correction. The measured CO2 is already at 7% O2, and because the percent of CO2 is not given for either CO or CO2, we have to use the O2 in this calculation. So, to fill in this equation, we can substitute the term Cp, with the 250 parts per million, since this is the existing mass of the particulates per unit volume of dry gas for CO. And in the problem statement, we can see that that measurement was made at 10% O2, but the EPA requires results reported at 7% O2. Then we can subtract 10 from 21 due to the percentage of oxygen in the CO. This is how we will normalize this term to the required 7% oxygen reporting requirement. So we'll have 14 on the top here, and 21 minus 10 for the 10% up here in the CO. Solving this out, we will get just about 318 parts per million. This is how we will normalize this term to the required 7% oxygen reporting requirement. Once this is done, we can go back to our combustion efficiency equation and plug in our terms for both CO2, which was given already, at the correct percent of O2, and the CO, which we just calculated. So let's replace CO with 318, and if we solve this out, we can get a combustion efficiency of just about 96.17%, which is closest to our answer number 2 on the left-hand side. So yes, this problem can look confusing at first, but once you realize that the correcting gas streams equation exists, and that it's perfectly fine to drop the CO2 term when the problem gives only oxygen percentages, it turns into a very simple two-step calculation. And that's it.